Page 54, we are going to finish up lesson 1.8, which is on using powers of 10 to estimate quantities. So on the do you understand, if we look at number 2, Kim writes an estimate for the number 0.00436 as 4 times 10 to the third. Explain why this cannot be correct. The reason this can't be correct is because if we multiply by 10, that would move our decimal to the right 3 spots. In this case, we need to move our decimal to the left 3 spots. So this would actually be, should be 4 times 10 to the negative third power as an estimate, okay? The exact would be 4.36 times 10 to the negative third. Again, the idea is if it's to the negative third power, if we put it in the opposite part of the fraction, makes it a positive exponent. When you divide by 10, that moves your decimal to the left. If we look at number 3, Raquel estimated that number as 3 times 10 to the 8th. What error did she make? What we're going to do is just look at the decimal would start after the last digit. If we move it right after the 3, 6, 9, 11. That moved 11 places. So that should have been like 3 times 10 to the 11th power instead of 3 times 10 to the 8th power. Okay, so we could just say she had the wrong exponent. Should have been 3 times 10 to the 11th power. Look at number 4. Use a single digit times the power of 10 to estimate the height of Mount Everest to the nearest 10,000 feet. Okay, so Mount Everest, it's between 20,000 and 30,000 feet. To the nearest 10,000 feet, we would round it to 30,000 feet. And then basically putting it in scientific notation, we want just one number that's not 0 and then the decimal point. So the decimal would have to go right after the 3. So we could say that's the same as 3 times 10 to the 4th power. Decimal moved 4 spots, so we would have to multiply by 10 4 times, would move our decimal 4 spots to the right. If we look at number 5, this is the reason they use scientific notation. It's really hard to keep track of how big or small these numbers are like this. So scientist records the mass of a proton as that part of a gram. Use a single digit times the power of 10 to estimate the mass. Okay, so we are estimating, if you'll notice, the first number we have that's not a 0 is the 1. After the 1, we have a 6. So the decision is whether we keep it a 1 or do we change it to a 2. Since the 6 is at least a 5, if it's 5 or higher, we're going to round up. We're going to change that to a 2. Rather than rewriting all of this stuff, I'm just going to put a 2 there and kind of cross out the other stuff because it's hard to keep track of all of that. So then we're just going to see if the decimal goes from here all the way after that 2. We're going to see how many spots we move that. So what we can do, if you want to, go in sets of 3 to make it easier to count. So 3, 6, 9, 12, 15, 18, 21, 24 places, okay? Maybe counting by 5s would be easier to keep track of for future reference. But anyway, so that would be 2 times 10. And we moved it 24 places. The question is it 2 times 10 to the 24th or is it 2 times 10 to the negative 24th? And it would be to the negative 24th. Remember, small numbers are going to have small exponents. They're going to have negative exponents for numbers less than 1. Big numbers are going to have big exponents. They're going to have positive exponents. Number 6, the tanks at the Georgia Aquarium hold approximately 8.4 times 10 to the 6 gallons of water. The tanks at the Audubon Aquarium of the Americas hold about 400,000 gallons of water. Use a single digit times a power of 10 to estimate how many times greater the amount of water is at the Georgia Aquarium. Okay, so what we can do is a couple different ways we could do this. One way would be we could get these both as regular numbers. The other way would be we could get them as scientific notation. And maybe I'll just mention both ways to you. So one way would be 8.4 times 10 to the 6th. If you take the decimal was here, and if you move it 6 places to the right, that would be the same as 8,400,000. So 8,400,000 gallons for the Georgia Aquarium. The other one was 400,000 gallons. So to figure out how many times greater one thing is than the other, we can divide. So if you divide that, if you would just do that on a calculator, we could do that. And what should happen is it should come out up as being 20. So that means 20 times greater, which is normally what we would do. It says use a single digit times a power of 10 to estimate how many times greater. So instead of 20 times greater, we could say 2 times 10 to the first power, or just 2 times 10. Probably we'll put it as, I guess, 2 times 10 to the first power. Okay, so that would be one way of doing this. Another way, if you get the hang of this a little bit, and then also especially if you don't have a calculator, another option would be get both of these in scientific notation. So one's already in scientific notation. The 400,000, so that'd be 4 times 10 to the 5th power. And then what we can do here is we're actually allowed, since these are being multiplied, we're allowed to kind of split this up as 2 separate fractions. And if I go back, then I can see I made a mistake then on that last part. We'll look at that in a minute. If you divide this out, 8 4/10 divided by 4, you'll get 2 1/10. And then 10 to the 6th divided by 10 to the 5th, that's like we did earlier. We divide like bases, subtract exponents. So that would be 10 to the 1st power. And what we can do is write it this way. So 2.1 times 10 to the 1st power. So going back to what I did in the first part, this actually would have been 21 times greater, and so that would be the same, would be 2.1 times 10 to the 1st. I was just looking at the book's answer they had as being 20 times greater, but it's not quite exactly. It's actually 21 times greater. And it already says approximately, so that's would be one option. The other option, I guess as a third option, would be 8 4/10. You could say that's about 8, and then 8 divided by 4 is 2, and then that would come out exactly as 2 times 10 to the 1st. So either of those ways, either of those answers would be fine for that one. So look at workbook page 15. They want us to use powers of 10 to estimate So number one, use a single digit times the power of 10 to estimate that number. So rounding to the nearest millionth, first of all, looks like we've got, after the decimal, there's 5 zeros before the 7. The question is going to be whether we keep that as a 7 or we change it to the 8. So look at the number behind it. So since after the 7 we have a 3, it's not a 5 or higher, we're going to go ahead and just keep that as a 7. So this is apparently 7 millionths. And then we're going to write this in scientific notation. So right now, the decimal's not where I want. I want to have a number that's not 0 and then the decimal point. So let's think about how many times we have to move the decimal to get it there, first of all. So that would be 6 places moving the decimal. And so we're going to put this as 7 times 10 to the negative 6th power. Negative 6 because, again, this is a small number. It's like we're dividing by 10 6 times. Every time dividing by 10, moving the decimal to the left. Again, we're not going to write it this way, but this is equivalent to that. Remember, negative exponent, put it in the opposite part of the fraction. And again, dividing by 10 moves to the left, multiplying by 10 moves it to the right. So small numbers, negative exponents, big numbers, positive exponents. If we look at number 2, city has a population 38,802,500 people. Estimate the population to the nearest 10 million. So this is between 30 million and 40 million. After the 3, there's an 8, so that means we're going to round up. It's closer to 40 million. And then they want us to write this basically in scientific notation. So right now our decimal's after the 0. So we want to get this decimal right after the 4. We want one number that's not 0, then the decimal. And so that would be 7 places moving. It would be 4 times 10 to the 7th power, because we're going to multiply by 10 7 times, moves our decimal 7 places to the right. Number 4, according to a survey, residents of country A have approximately 179,300,000 dogs and cats as pets. The same survey reports there are about 5.01 times 10 to the 7th dogs and cats as pets in country B. So the question is about how many times greater is number of dogs and cats in country A than country B. Alright, so when you guys are doing these problems, again, probably not a bad idea to underline or highlight information. I did it in different colors here, so if you want to have different colors, if that makes it easier for you to look at the different parts of what the information is that's being given. So like we mentioned earlier, a couple options of doing this, and we're just going to estimate this. We're just going to round these off a little bit here, I guess. So let's just round this off for country A. Let's just go to the nearest 100 million. So that we could round to 200 million. And then we're just going to go ahead and put that in scientific notation. So that'd be 2 times 10 to the 8th power. Again, our decimal's here. We want it to be here. So that's 2 times 10 to the 8th. We're going to figure out how many times greater the one is than the other. So we're going to divide. If you'll notice, 2 times 10 to the 8th. This one's times 10 to the 7th. If it has a bigger exponent, it's a bigger number. And then also what we're going to do is we're going to round that number as well. So we'll just say that's about 5 times 10 to the 7th power. And then what we can do, like we talked about earlier, we can split this up as two separate fractions, kind of. So 2/5 times 10 to the 8th over 10 to the 7th. 2/5, if you divided that out, or you may just know this, that's the 4/10, 0.4, if you divide that. And then with these, we talked about dividing that before. So dividing like bases, subtract the exponents. 8 minus 7 is 1. So that'd be 10 to the 1st, which is just the same as 10. And then 4/10 times 10, we don't need to break the calculator out here. Multiplied by 10 just moves your decimal one spot to the right. So that would be the same as 4. So we could say it's about 4 times as many. Okay, and again, complete sense, we could talk about country, whichever one it was. Country A had about 4 times as many cats and dogs as country B. Number 11, an astronomical unit, AU, is equal to the average distance from the sun to Earth. An astronomical unit is about 92,955,807 miles. Oops. Use a single digit times the power of 10 to estimate this value to the nearest 10 million miles. So let's go ahead and round this first, and then we'll do the scientific notation, what they're asking us to do. So this is between 90 million and 100 million. It's closer to 90 million miles. And then we're going to write that in scientific notation. So our decimals here, we want it to be right after that 9. It's a big number. It's going to be a positive exponent. That's moving the decimal 7 places, so this would be the same as 9 times 10 to the 7th power as our estimate. And then part B, Venus is about 7.2 times 10 to the negative 1st astronomical units from the sun. Mars is about 1.5 astronomical units from the sun. Which planet is closest to the Earth? So if we look at this, 10 to the negative 1st means we move our decimal 1 place to the left. And for Mars, it's already there. So from what they told us at the very beginning, I was missing out on this fact, but this is saying that the Earth is on average, 1 astronomical unit from the sun. So at that point, what we could do is see how far away these are from each other. So if we have 1 minus 72 hundredths, see what that difference is, which would be 28 hundredths AU, and the other one would be 5/10, or if you want to add a 0 on that, you could be 50 hundredths. So you can see that 28 hundredths is less than 50 hundredths, so that means Venus is actually closer to the Earth than Mars is. So why we don't have missions to Venus probably would have to do with going closer to the sun. Would be a lot hotter and pretty dangerous expedition for Number 12, the oldest rocks on Earth are about 4 times 10 to the 9th years old. Which of these ages could this be an approximation? Select all that apply. So basically, if we were rounding, which of these would we round to 4 times 10 to the 9th? So for the first number, we've got a 3 after it's an 8, so we would round that up to a 4 with a bunch of zeros after it. And then think about if we were putting this in scientific notation, we'd move the decimal 9 spots. This is a big number, positive exponent, so that works. The second one is almost identical because there's a 4, but after it's only a 1, so that would also round to 4 billion. So that would work as well. I'm not even going to look at the next one. That's a really small number. That would be a negative exponent. So I don't even care how many spots that is. The next one, after the decimal, there's a 4 there. So that's not quite there. We don't like round and then round the next number. We just look at the number right after it. So that's actually closer to 3 times 10 to the 9th. It's pretty close, but not quite there. And then the last one, after the decimal, we have an 8. So that would go closer to 4. And so that would work as well. So this gives you an idea of how to use powers of 10 to estimate quantities.